Okay, hello, this is Dr. Muhammad, and this is another class under Dynamics of Structures. And today I'm going to talk about some examples on undamped free vibration response of single degree of freedom system. So this is the title of our class for today. We are going to apply what we have learned in the previous lectures on real examples today. Okay. Before going into the examples, I'd like to highlight an important concept that is going to help us in our examples in general. First of all, we want to place emphasis on the relation or the main components of the system, which is stiffness, damping, and mass components. And we want to relate every one of them with one component or engineering demand parameter of the system. So we can say that under the action of external force, whenever that we have a system, as you can see here, and we have an external force applied in it, okay, which is P of t, means that it is changing with time, okay. So the state of the system is described. So we can describe the state of the system for the single degree of freedom system is described by displacement, velocity, u dot of t, and acceleration, u double dot of t. So we have like three main components, okay? Three main components. We are going to map these three main components to the main components of the system, which is related to the stiffness, damping, and mass, the main characteristic components of the system. Okay. Okay. So now the external force, which is Fs on the stiffness component, is related to the displacement. Okay. To the displacement u if the system is linearly elastic. So we are going to say that our system, which is applied, or there is force applied on it, which is changing with time, it is equivalent to a system that is having the stiffness and does not have any damping and does not have any mass, and applied on it by external force Fs or Fs. This is the elastic force. We're going to presume here, this is a kind of perspective of our system to understand it. So we're going to assume that our real system is composing of three different systems. Each system of them is applying, or there is one component is being applied on the system and giving us or relating or related to a certain engineering demand parameter. So we're going to assume that our system equals to the system with stiffness, without mass and without any kind of damping, and applied on it, or we apply on it, Fs. In this case, this system is related to, or this force is related to u, the displacement of the system. Plus another system which does not have stiffness and does not have mass, but it does have the damping. So we're going to apply, as if there is force being applied on the system, Fd, and of course the system is going to resist it with the same magnitude and in the different direction. And this component is going to be related to the velocity, u dot. Okay? And then we are going to say that the mass, the last component that we were talking about here, the mass, is going to be in a system that does not have stiffness and it does not have damping as here, but it is going to be under force called Fi, which is the inertia. And this inertia is going to be related to the acceleration of this mass. So we can look to our system as it is, the real system is here, that is a system that is having a stiffness, damping, and it has mass, of course, and there is a dynamic load being applied on it, and we have three different components or engineering demand parameter that we want to obtain, U dot and U double dot. Then this system is going to be equivalent to three different systems. The first is related to the elastic force, which can be mapped to the displacement. The other system is going to be the damping force, which can be mapped with the velocity. And the last one is the inertia force, which is going to be mapped to the acceleration of the system. So the superposition of these three systems, or addition of these three systems, is going to give us the original system that we are seeking for. Okay? So this is important concept that is going to help us in solution in general. Okay. Now let's go to the example number 1, and let's see how we are going to solve and deal with it. Let's read the example first and try to understand more about it. First of all, we have a small one-story industrial building. So first of all, I want you to analyze whenever that you are reading any example or any problem, I want you to analyze the wording in the example, because there are keywords that is going to guide you to the right solution at the end. So first of all, we say that a small one-story industrial building. One story means that we are talking about single degree of freedom system. Okay? So it's not multiple or not multi-story. It is only one-story industrial building, which is 20 by 30 foot in plan. So the plan is, as you can see, 20 feet here by 30 feet. Okay? This is the plan that we have, as we can show, as it can be shown in this figure E 1.2. You can find this example in Chopra book. Okay, with the moment frames in the north-south direction and braced frames in the east-west direction. So we have here, this is the north direction, as we can see. In this direction, we have, as they said, moment frame in the north-south direction, which is the vertical direction here. Okay, we are having moment frames in the north-south. So this is here, here, and here. We have moment frames, and these moment frames are going to be, this is the direction, the long or 30 feet direction, as you can see it here. And we have like moment frame here, and we have roof truss. Okay, here. The height of this moment frame is 12 feet. And in the shore direction, which is the 20 feet direction, in the X direction here, we have braced frames, as you can see it here. In the shore direction, which is 20 feet, we have this bracing frame. We call this is vertical bracing. Okay, so we have two different systems in each direction. Okay, we have two different systems in each direction. The weight of the structure can be idealized as 30 pounds per foot square, lumped at the roof level. Actually, commonly in these kind of industrial structures, we can say that the weight per unit area of the roof is given by a value which is like 30 pounds per foot squared here, lumped at the roof. This means that if we are going to calculate the total mass of the whole roof, then we're going to multiply this 30 pound per foot squared times the total area, which is 20 by 30 feet. Okay? Okay. So take care, this is lumped at the roof level. Do you remember that when we were talking about the types of masses and we mentioned about lumped? So our system is going to be idealistic for single degree freedom system, which is going to be lumped at one point. The horizontal cross bracing is at the bottom chord of the roof truss. So we have like horizontal, so we have the horizontal cross bracing. We have cross bracing supposedly to be here and here, which is going to resist any lateral force in the plan, okay, in the plan of the roof here. The horizontal cross bracing at the bottom chord of the roof trusses. So as I indicated here with the red lines. All columns are wide flanges, 8 by 24 sections. So we have 1, 2, 3, 4. We have 4 columns. All of them, they are wide flange with this cross section, which is 8, okay, 8 by 24. Okay. Their second moments of cross-sectional area about x and y axis. So we have ix and iy. So we have ix and we have iy. So everything about the section is already known for us. Okay, they are given here respectively. Take care of one thing, and the numbers are telling us something here. That ix is 82. Almost 82 something, and iy we're talking about 18 something, okay, right? So this means that we are having ix, this is xx here, and this is yy. Commonly, the section is going to have bigger inertia around this xx axis, right? So here we are having the bigger inertia around xx. So we are going to consider, and this is why the moment frames are arranged in the north-south direction, okay? However, in the east-west direction, you're going to find that the inertia of these columns are negligible. It is small, okay, because it is 18 only. Okay. For steel, we have 29,000 KSI, which is Young's modulus of steel, constant for all types of steel. The vertical cross bracings are made of 1-inch diameter rods. So here, these are the bracings here, and they are made of rod. This rod is 1-inch diameters, okay, diameter. So what we need from this? Here in the example, they said that formulate the equation governing free vibration in north-south direction and east-west direction. So we want to write the equation that is governing the free vibration. What is the equation of motion for these or for these two directions that the system is going to behave in the north direction and the east direction. Okay. Now first of all, I'm going to put again what we have. Let me summarize what are important things that we have here. So first of all, we're going to assume, okay, even that it hasn't been mentioned in the example, assume that we're talking about undamped system. Okay, so this is number one. Let's go back, check again for this system. There is nothing mentioned here about this. A small one-story industrial building shown blah 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 moment and braced frames here, the horizontal, and then giving everything, but we are not being notified regarding whether it is damped or undamped. Okay. So here I want to highlight one thing which is important. Whenever you assume that the system is undamped, then by default you're going into what you have studied in the undamped system. Okay? So you need to remember what we have explained regarding it. Okay. After that, we need to put that the I column we have like Ix and Iy for the column is given for us 82.8 inch to the power 4 here and 18.3 inch to the power 4. And then we have the Young's modulus of steel is given 29,000 KSI. These are going to be important numbers for us when we are going to solve. The rod is 1 inch diameter, so we have like 1 inch diameter. This is going to be the diameter of the rod. Okay? Okay. Then the weight of the structure, as it has been given for us, it is, take care, they are like giving us the weight, which is going to be 30 pound per foot squared. Okay? So this is lumped at the roof level as it has been given. Okay, so these are the important things. Let's assume undammed system, and Ix and Iy, we know it. Another important thing is that this system, we have like the system is having a roof truss. This roof truss is going to be dealt with, okay, the roof truss that we have here is going to be dealt as rigid, okay, rigid diaphragm. Okay, so here, this is what we have mentioned here. It's a rigid diaphragm, okay. So whenever that we are going to deal with it, this means, what is the meaning of the word rigid diaphragm? It means that there is no local deformation on or in this system, and all the horizontal loading are going to be, all the horizontal loadings or forces are going to be like distributed, okay, to the main supporting system, whether it is a braced frame, or if we are talking about the east-west direction where that we have the bracing, okay, we have the bracing frame. So this means that our system, whatever the system is, the roof is rigid, so all the mass is going to be concentrated here, and it is going to be rigidly transferred to the main lateral force resisting system, whether it is moment frame or braced frame. Okay, so this is the meaning of rigid diaphragm. Okay, now the first thing, let's put what is the sequence, or what is the sequence of our solution. And before that, we need to determine the following. Number one, in order to go, we want to formulate the equation of motion, right? But before going into the equation of motion, we need first to know what is the natural circular frequency, right? All of our equation of motion, if you go back to the previous video, you're going to find that omega is going to be there, right? So this means that we need to know what is omega. And number two, we need to know what is the natural cyclic frequency, which is going to be natural period T, okay, of the system, and they are dependent on one another. And three, we need to know what is, sorry, this is not the natural, this is the natural, I'm sorry, this is F, okay, the natural cyclic, it is Fn here. And three, we need to know what is the natural period of vibration. Period of vibration, okay? We need to know this is, which is T. And after that, at the end, after knowing all of this, we need to know the equation of motion. The governing equation of motion, EOM, of the system. So if we could obtain these, and by obtaining the mass and stiffness of the system, then we can go and formulate our equation of motion in whatever direction that is required. Okay, so this is the strategy that we are going to follow. Okay, before going into anything, we want to know what is the mass of this system, right? It is given for us the weight. So the mass is going to be the area that we have, okay, which is 20 feet by 30 feet, times the unit weight, okay, the unit weight of the area, which is already given as 30 pounds per foot squared, over the G, which is, this is G. Our case, G is going to be 386, right? This is inch per second squared. So we are like having this 30, it is already given. This is, as we said, it is pound per foot squared. And this is 20 by 30, it is the area of our system, the area or the plan of our system. And then if you multiply, take care of the conversion here, because we have inch here, and this is there is foot here. So after conversion, we're going to find that our mass of the system is 46.63 in pound second squared per inch. So this is our mass. This is the mass of the system. Okay. Again, this is considered to be as if that we are having concentrated mass here. This is the concentrated mass of a single degree of freedom system. Well, now we are getting closer to what we have explained in the previous lectures. Okay. The second is we want to know what is the stiffness of our system, of this single degree of freedom system. Okay. But according to our problem, we have two directions, right? So here we have two directions. We have like the short direction and we have the longer direction, east-west and north-south. So this means that we're going to have two types of K in each direction, and we need to study it independently. Okay, so based on this, we're going to say, let's start with the case A, which is north-south direction. North-south direction. And let's see how we can understand this. So first of all, what is the K and S? What is the stiffness in the north-south direction? It is going to be, actually we have like four, right? We have like four columns, if you remember, so we have something like this. We have four columns here. So in this direction, which is the north direction, we are having four columns. So we're going to multiply 4 by, do you remember when I was assuming fixed condition? Do you remember this? When we have a fixed condition, we said that the shearing or the shearing force that is going to be developed if this system is going to move, the shearing that is going to be developed here equals to 12 EI over h to the power 3, right? This is the stiffness, the shear stiffness. So our system, we're talking about this, whenever that it is going to move under the ground excitation or whatever the force that is being applied, it is going to make something like this. Okay, this means that the system is going to, as if that it is fixed from the top and fixed from the bottom. So this means that it is fixed condition, and we have four columns. We have four columns. This means that we are going to multiply by 12 EI over h to the power 3, right? This means that we have 4 here, and then we have 12 in the numerator multiplied by E, which is 29 times 10 to the power 3, as we know, and times I, which is the larger I, exactly 82.8, right? This is going to be over 12 feet, which is the height of the column, 12 feet, but we're going to convert it to inches, so we're going to multiply by another 12 here. So this 12 for conversion. Then we're going to find that the value for K and S is going to be 38.58 kips per inch. Okay, kips per inch. This is the stiffness. So this means that the K N S is going to be, the value is 38.58. Okay, kips per inch. Let me check something here. This is the value that you can see in the solution. Okay, it is going to be 38.58 kips per inch. Kips per inch. Okay, now this is the stiffness of our system. That's very nice. Now let's go to the next part, which is related to the equation of motion. Okay, and know what are the missed parts that we want to have. So the equation of motion, okay, the equation of motion for this system, it is undamped system. So we're going to have m times u double dot, and there is nothing related to u dot because it is undamped system, plus k, in this case it is going to be ns, which is north, south, times u equal to 0, right? This is our equation of motion that we want. But again, we know m and we know here k, so everything is going to be okay for us now. We can put this system or put the equation knowing m and k and s for the north-south direction. But we are going to determine other parameters, which is omega and the frequency, or omega and f and t, in order to make a comparison that is important for us between the north-south direction and the east-west direction. Okay, so first of all, omega, natural circular frequency, omega n equals to the square root of k over m, right? This is what we have explained last time. And based on this, we have like k and we have m. M is 46.63 and k it is 38.58. We're going to multiply by 1000 here to convert it from kips to pounds. And then we're going to find that it equals to 28.73. 28.73, and this is going to be in rad per second. Okay, this is what we call it, the natural circular frequency. The natural circular frequency. Okay, the natural circular frequency. Well, okay, then for Tn, which is the natural period, is going to be 2 pi over omega, and it equals to 2 pi over this omega that we have obtained shortly. This is 28.73, and this equals to 0.219, okay, second. And this is what we call it, the natural period. This is the natural period. Okay, and then we have Fn, which is going to be 1 over Tn, right? And it equals to 1 over what we have obtained here, which is 0.219, and this equals to 4.57, and this is going to be in hertz, right? And this is what we call it, the natural cyclic frequency. The natural cyclic frequency. Okay, now we have these values. I'm going to highlight these values because I'm going to compare at the end these values with the other directions. So we have here, this is the omega n, this is Tn, and this is Fn. Okay? Keep it in our mind. These are the characteristics of the system in north-south direction. This means, what is the meaning of the characteristics of the system in the north-south direction? This means that our system, if we have this is the system here, our system, its characteristics in this direction is going to be totally different than the characteristics in this direction. So x direction is different totally in y direction. Is it true? Yes. If we are going to study the system in this y direction, we're going to find that its Tn is 0.219. 0.219. Its natural period is going to be like 0.219. We're going to study it in the x direction or east-west direction. Let us see how it will work for us. Okay, now let's go to the next part, which is related to the east-west direction. Okay, let me use the same. So let's put here the east-west direction. So this is the second part. And in the east-west direction, we said that we are dealing with braced frame, right? So we are dealing with the braced frame. Actually, we have like two systems here. So our system, this is our main system, okay, that we have here. Okay. So we have cross bracing here. So this system is equivalent to two different systems. The first one is going to be like the cross bracing. So we have like the cross bracing here, plus another system which is going to be the like moment frame, but the moment frame is going to be not working for us. Why? Because the column cross section is oriented in this direction. This means that the lateral resistance of this frame is going to be negligible. So based on this, we can say that we are going to neglect the contribution of the columns because of their moment of inertia of the cross section, or the moment of inertia of their cross sections is going to be small and not going to control in the system. So we are going to use only the bracing system that is going to be working for us. Bracing system, okay, not the rigid frame. Rigid frame contribution is going to be neglected or going to be negligible. Okay. So we can write this note, and it is going to be beneficial for us. That is note here, which is the rigid frame stiffness. Okay, the rigid frame stiffness can be neglected. Can be neglected because the inertia of the columns are small. Okay. So we can say this is an important note. Whenever that you have a system that is containing two different subsystems, then you need to know which system is going to contribute high in your inertia. Okay, so in our case, the rigid frame will be negligible. However, the bracing frame is going to work well. And I'm going to like prove this at the end using the numbers that we have, okay, at the end. Okay, so now we need to know, the equation of motion. And before this, as we said, we need to understand what is the main system is going to, how the main system is going to behave. So let's go and see in our equation of motion. Commonly, the equation of motion is going to be, as we have mentioned before, it is going to be mu double dot plus ku equal to 0, right? This is the equation of motion, and there is no term for the damping here, right? This means that we need to know what is m to put it, what is k that we should put. In this case, k is going to be east, west, okay? So we need to know what is the east-west stiffness that is going to be present in this equation. The mass, already we have explained the mass, and we have obtained the mass from the previous slide. Okay. Now let's go and understand more about the axial stiffness of the brace, and understand how that we are going to deal with it. So let's here talk about the axial stiffness of the brace. We want to know more about it. So if we have a brace, okay, this is the bracing here, which is having A and E, cross-sectional area and Young's modulus. Whenever there is movement, lateral movement, what will happen is, under the lateral movement, this system or this brace is going to move here, right? And the point is, the distance that is going to be between the original one and this one is going to be u. This is the point of the system where that before and after movement, okay? Our system, remember that our system is something like this, okay? And the point is, whenever it moves, so actually this bracing, whenever it moves, it will move like here. So we are going to have our new bracing. It is going to be a little bit elongated, right? So that's the point here. In this direction, this is u. However, the force that is being applied on the system, is going to be, or in the brace, it carries only axial force, right? So we're going to have like P here, which is the axial force, and it makes like theta, okay? Theta prime, for example, here, which is with the horizontal. And we are going to have this distance, which is the elongation in this brace, is going to be called delta, for example. Okay? The relation or this angle of the brace with the horizontal, we are going to give it a name like theta. And the distance between the two nodes here, which is the length, we're going to designate it with L. Okay? So the axial stiffness of this bracing is going to be, axial stiffness, okay, of bracing. We are talking about bracing here, okay? It is going to be P, which is the force applied on delta. We're talking about axial stuff, so we're talking about delta here, P over delta. And this is commonly, from statics, we know it, that it equals to EA over L, right? So this is the axial stiffness for us. So from statics, we can say that Fs, which is the horizontal component here of this force, we call it Fs. Why Fs here? This is the horizontal component of P. This Fs is the horizontal component that is going to make lateral movement of this point, okay, which is actually our main concern. So it is going to be this Fs equal to P times cosine theta, okay, theta like prime here. It is going to be different than theta, okay, but very small because these deflections are very small, so theta prime and theta, they are going to be almost the same, okay? So we can say that theta almost equal to theta prime, okay? These distances are very small, negligible, okay? And from kinematics, we can say that U here is going to equal this delta over cosine theta, right? Theta, this is delta. And we have this U, so we have this relation between delta and U, which is delta over cosine theta. Okay, now, K for the bracing, K for one bracing is going to equal P over delta, which is as we said here, which is EA over L, right? And then we're going to substitute with what we have done. So it is going to be Fs over cosine theta times 1 over U cosine theta, right? We didn't do anything. That if you look here, I didn't do anything. This one, it is P, right? And this one is 1 over delta. So it is, we are right. So here we can say this equals to, at the end, we're going to find that Fs over U times cosine theta squared. Cosine theta squared. Okay. So if from the geometry you can find that cosine theta equals to 0.85. Okay, 0.85. This is from geometry. Okay, you can find that it equals to almost like 20 over the square root of 12 squared plus 20 squared. Okay, can't find it. Cosine theta is known for us. Okay, now we can say this is the axial stiffness, but we are interested in something else, which is what? The lateral stiffness. So K bracing, this is K, which is axial. And then I'm going to write K bracing, which is lateral. Lateral. This lateral is the most important thing for us, for the frame, and for us, we want this lateral direction. What is the deflection and what is the resisting forces here? So K bracing lateral is going to be the important thing for us, and we can say it equals to F of S over, or Fs over U, which is the force here, Fs over U. How much? So like we have Fs here, and this displacement is going to be U. So this is the lateral displacement. So we can write that from here, Fs over U is going to equal, so we have the equation here, we can get Fs over U. This part here, we can obtain it if we are going to substitute with EA over L. So we can find that it equals to EA over L cosine squared theta. So we have, this is the equation that we have right now, K bracing lateral. So what is the meaning of this and why we are going into these kind of calculation? The point is, at the end, we want to know that Fs over U is going to be determined by like some known parameters. We know E, we know the area or cross-sectional area of the brace, we know its length, we know cosine theta as cosine theta as we have obtained it here. So everything is known for us. We're not going to calculate anything, it's known for us. So we can obtain this K lateral bracing. We are interested in this lateral stiffness. This is, we can write this, we are interested in this, okay, in this stiffness, which is the lateral stiffness. Take care of this. We are interested in lateral stiffness, not in the axial stiffness. Why? Because the lateral stiffness is our main concern for the equation of motion. If we go back here, the equation of motion, that here K means that how much the system is going to find resistance for the mass when there is forces being applied here. So we want to know the shearing resistance here. Okay, that's what we are concerned with. Okay, so now let's assume, or let's go and calculate what we have obtained here, EA over L times cosine square theta. So we can put it in straightforward. So here it is going to be K bracing, okay, which is K for bracing lateral now. We're talking about lateral. This is our main concern. So it's going to be 29 times 10 to the power 3. This is our E times A, 0.785. This is inch squared. From where it is, we have a rod. We have a rod. This rod is 1 inch diameter, then you can obtain the area easily. Over the length, okay, which is going to be 23.3, and we will multiply by 12 in order to convert to inches, okay, and then multiply by cosine theta squared, which is 0.85 to the power 2. This gives us at the end 59.8, which is going to be in kips per inch. Okay, kips per inch. Okay, so the point is, this is what we are going to have. I want to highlight one note here, which is considered to be suitable to be highlighted. Okay, which is the brace in tension will provide the lateral force. Here, if you look, in my calculation, I said that this brace, if it is the force is being applied in this direction, then this brace, which is going to be in tension, is going to deform and making this lateral deformation new. But I didn't mention about the buckling of, or the other one, which is going to be definitely in compression, right? Why? Because we are assuming that this rod is not going to resist anything in compression. It is a rod 1 inch diameter. Can you imagine? So buckling will not work for us, and if there is resistance from buckling, it would not be that big. It is going to be negligible. So we need to put it as a note here, and we are going to say only brace in tension, only brace in tension will provide the lateral stiffness, the lateral stiffness of the brazed frame. Okay, the compression, the compression brace will buckle. It will buckle. Okay, so it will not help us in our system. It will not help us in our system. Okay. Based on this, if we have this 58. Our system, so K, can say now, K of the whole system in the east-west direction is going to be how much bracings that we have. Actually, we have two bracings. If we go back, right, we have like one bracing here and another bracing here, right? This means that we are like having two main resisting system here coming from the different two bracings. So we are going to multiply this 59.8, we're going to multiply it by 2, and this would give us 119.6 kips per inch. Okay, so this is EW, or the east-west one. Let's make a very small exercise regarding showing. Do you remember when I was telling about the rigid frame that is not going to contribute, and I put a note here? No, I'm going to I put a note here that we said that the rigid frame stiffness can be neglected because the inertia of the column are small. Do you remember this? Because the inertia here we said is very small. Let's check it now by numbers. So let's assume that what is going to be the contribution of column. So let's assume what is K column is going to have. So we have let's assume that we have here 4 columns, right? We have 4 columns here. Let's go back here. We have 4 columns, 1, 2, 3, 4. So we're going to multiply our 4 columns by the inertia of 1 column only, right? Which is 12 EI over the height of the column, which is going to be h to the power 3, h to the power 3. If you calculate it, take care that we are going to talk about IY here. So in this case, you're going to find that we multiply 4 times almost 2.13 for 1 column in the weak direction, and the total is going to be 8.52. Okay, 8.52, which is going to be also in kips per inch. Can you compare this? 8.52 with almost 120 kips per inch. So this means that we can confidently, or we can neglect this. Okay, but if you want to be very accurate, you can use it also. Maybe it will contribute a little bit, but again, it is very small, and we are going to be conservative and not using this stiffness coming from columns. Okay. Now let's go to something that is interesting also, which is related to some numbers related to the east-west direction. So we're going to calculate omega n. In this case, it is going to be the square root of 119.6 over 0.04663. This is the mass after being converted. So we're going to find that we are having 50.64 rad per second. And then our natural period is going to be 2 pi over this 50.64, and it is going to give us 0.124 seconds. And for the natural cyclic frequency in this east-west, it is going to be 1 over 0.124, and this gives us 8.06 hertz. Okay? Okay, now let's go and analyze this. So here, this is for the east-west, right? We're talking about the east-west direction here. What you can see here, omega n is 50 something, and here we have t.124. Do you remember the other one, how much? In the other direction, it was 0.219. 0.219. Here it is 8 hertz. here it was 4.5 hertz. What is the meaning of this? If I'm going to compare based on only the t, okay, only t, 0.219, okay, 0.219. This is for the north-south direction. What is the meaning of this? Let's go deeper into the numbers and understand what is the meaning of 0.124 and 0.219. This means that the natural period of the system in the north-south direction is going to be longer. So if we're going to put the system here, so for example, if it's like single degree of freedom system, this is from here to here, it is going to be 0.219. However, our system, this system, okay, is going to be much less, almost half of it. Almost half of it. If we're going to make something like this, it is going to be half of it, for example. Okay, let's assume. So 0.124. This means that because this system, or we can say this system is stiffer, so its natural period is lesser than the natural period of the other direction. This gives us the meaning that there is a relation, as we said always, that omega is related to the square root of k over m, and this omega equals to 2 pi over Tn. So this means that when Tn is going high, k definitely is going down. Okay, so that's the meaning here. The two systems are opposite to one another. We have one system that is its period, natural period is higher, and the other, its natural period is lower. Okay? Okay. Okay, now let's go to the last part and finalize this example. Okay, we can say that the frequency, as you can see here also, that the frequency, natural frequency of the east-west is larger than the frequency of the north-south. Why this is the reason? Why the reason for this? Because the braces make E or east-west stiffer even if the columns are in the weaker direction. So if we are going to put a justification for this, we're going to say that in the east-west, the braces, okay, you can put it here, the braces are making it stiffer. That's the main reason. Okay, the braces make it stiffer. Okay, as it can be seen that the natural frequency and period does not depend on the initial conditions of the system at all. Okay, as we have mentioned before in the previous lectures. I hope that you have understood this example, because really it is an important example. It gives you an understanding of what we have explained before in a physical sense, based on something that is really going to help us for understanding how the single stories are going to perform. Okay, now let's go to another system, and let's go to another example, which is example number 2, and let's see how we can deal with it. It's going to be straightforward also. So in this example, we are going to have a bridge, box girder bridge that is supported on 4 supports, as you can see. Its length is 375 foot long, and it is concrete box girder bridge on 4 supports. We have 4 supports here, 2 abutments and 2 symmetrically located bins. So we have here, this is the abutment 1 and abutment 2, and this is the deck. Okay, and we have the direction here. This is X, the vertical is Y, this is the longitudinal, and here this is the transverse. The distance between the abutment and the supports is 125 feet. Okay, the cross-sectional area of the bridge deck is 123 feet. So the cross-sectional area of our bridge is 123 foot squared. The weight of the bridge is idealized as lumped at the deck level. It is similar to the previous example. The unit weight of the concrete is 150 pounds per foot cubed. And the weight of the bins may be neglected, so any bins here is going to be neglected. Only we are going to consider the mass of the bridge itself. Each bin consists of 3 25-foot tall columns of circular cross-section with IY prime and IZ prime equal to 13 foot to the power 4. Okay, so this is we're talking about the supports here. They have like similar K here, and the inertia is the same, and because they are circular, so we have IY and IZ to be the same. Formulate the equation of motion governing the free vibration in the longitudinal direction. So we are interested in this direction, which is the longitudinal. The elastic modulus of concrete is 3000 KSI. Okay, so now I think that it's very easy for us to write. What we want to do is putting the equation of motion first. Okay, so first of all, the weight per unit length of the lumped, unit length lumped at the deck level, we have the deck level is 123 times like 1 meter. This gives us 100 times 150, which is the concrete. As we have been given here, this is the related to the concrete weight of concrete, or unit weight of concrete, 150 given here. So we are going to multiply it by 1. So the total weight lumped at the deck level is going to be, this is per unit meter or per unit length, then this 18.45 is going to be multiplied by the length, which is going to give us these three, the summation of 125 3 times. So we are having the total length to be 375, and this is the total weight of the deck. Then from this weight we are going to obtain the mass. So weight over G, it is going to give us the mass here. Okay, so the G is going to be 32.2 and the mass is going to be 214.9 seconds squared per foot. The longitudinal stiffness of the bridge is computed assuming the bridge deck is to displace rigidly. Again, the word rigidly is going again to be repeated here. So it is rigid. Okay, rigid. The mass is going to be, the inertia force is going to be rigidly distributed among the supporting systems. Each column of a bin behaves as a clammed column. Clammed here means that as if it is fixed. Okay, so why he is telling us clammed? Because we are going to use a 12 EI over h squared. Do you remember 12 EI over h cubed? So here we are, this is the reason for telling us clammed here. It is like fixed. The longitudinal stiffness provided by each bend is, we have here 3, because he told us about this. Okay, we have 3. Take care, as I said, from the example, okay, wording. Each bend consists of 3 25-foot tall columns of circular cross sections. Okay, so we have here 3. And then the circular cross sections here that we have, it is going to be 12 EI over h to the power 3. Then we have 12 times E given for us, and IZ already given, times 13. So this is E for us 3,144, it's 12 by 12 for the conversion, and then IZ, it is given already 13 for us, the inertia of the cross-sectional, the circular one. And then h to the power 3, it is 25 to the power 3, gives us 12,940 kips per foot. We have two bends, provide a total stiffness, right? We have two bends here. Okay, we have two bends, as you can see. So this means that we have the total is going to be 2 times K bend, which is 12,940 times 2. It gives us 25,000 something kips per foot. The equation that is governing the longitudinal displacement is going to be mu double dot plus ku equal to 0. Then m, we have this m here, we can't put it here, this is a constant. And we have now k, which is going to be here. So this is the equation of motion, and these are the most important constants. U double prime and u, these are related to, yes, u double prime of t and u of t. This is related to the motion itself, which is going to be governed at every time. But we want to highlight what are m and k, what are the parameters that is going to be constant while that we are solving for this equation. Okay, this actually brings us to the end of this video. I hope that you have understood it well, and see you in the next video. Thank you.